Hello everyone, how's everyone doing today? Hopefully good. I got a couple of issues here. One of them is that I changed computers the other day to see if I can get rid of this problem. I've got a couple of problems. Sometimes it's a video problem, it's an image problem, and sometimes it's a sound problem. It goes into this buzzing mode. And if I get into that mode, please put a note in the comment section so that I can correct it. Okay, that's all I can do for now. I changed computers last time. It seems to be working better, but last transmission towards the end, it got a little fuzzy. The image got a little fuzzy. So just let me know. That's all I can do for now until I figure out. I don't know if it's the computers. There's probably some issue with the computers. There's also probably an issue with the software. So we'll find out. Maybe I can zero in on the problem someday and solve it once and for all. Got a couple of announcements. One of them is that here, I'll put it up. I'm going to be reminding people that we have the 7th Rational Physics Conference in Borås, Sweden. Okay, and that's going to be right now it's scheduled between the 6th and 9th of June. Okay, if there's any changes, we'll let you know. You can contact me through either the Facebook site or bill@youstupidrelativist.com, and we'll let you in on the little details, and I'll also be mentioning them through this channel as well. Okay, and that's the first one. The second one, and I'm going to repeat these if I remember at the end of the show today. Okay, and that's that I'm going to be on the 24th of June. What is it, of this month? I'm going to be in the public space again. There's a program run podcast by JFG, Jean-Francois Garipi. I think I'm pronouncing that name right. It's a French name, I assume. He's Canadian, okay, and he's in the area of Quebec. So I guess he speaks French. He speaks English with a beautiful accent. I love it. Anyways, I'll be on his program, JFG's program. Peter might join us. They told me he might be there, so it's going to be kind of interesting. And we're going to be discussing black holes. I think that's going to be the subject matter. If we have time, we might go into time, discuss time. And even if we have more time, which I doubt, but we might even discuss energy. Okay, so for sure, I think we're going to start with black holes. The reason for that is last time, when we had a little discussion there, JFG towards the end, brought up this issue about the black holes, and it's like we left it dangling there. We didn't really fix the problem. We didn't answer what a black hole is and what whether it's part of physics, whether we didn't solve the problem essentially. And so that's what we're going to be discussing, on the 24th. 24th, that's going to be, if I've got it right, 1900 hours Eastern Standard Time, which is Quebec time, okay? So if you're interested, just tune in, and you're going to hear a little debate or discussion on the subject. Okay, what am I going to do today? I'm going to continue a little bit with numbers. Some issues were not resolved last time. And again, they were left dangling there, I think. In other words, I think I need to tie some loose ends. And so in order to do so, I prepared a little discussion today on the subject. And that's going to lead us into the followings of the one that leads, the one that follows it, which is the point. Okay. Okay, so let's find out what is the problem. The problem with numbers has to do primarily with definitions and with the definition of number. I mean, if we're going to talk about mathematics, or even more basic yet, arithmetic, you're going to need to know what a number is. And the question is, whether we know what a number is. Last time we covered these subjects here, I'll put them up. And you can see that we have natural numbers, integers, rational and irrational numbers, real, imaginary, and complex numbers. Those are the primary ones, right? There are other categories of numbers. They talk about sets, they talk about fractals, they talk about manifolds, vectors, it just gets quite complicated in the field of mathematics. But these are the primary ones that people typically discuss. And the question is whether any of these meet the definition of number. And the only way we're going to find out is by defining what a number is, what the definition of number is. What do we mean by the word number? Okay. And so let's get on with that. Here I have a question that popped up. It's in the, what is it called? The Stack Exchange. And they asked the following question: what exactly is a number? Okay, I think it's a valid question. And the guy goes on to specify that, he says, we've been learning about complex numbers in class, and I don't really see why they're called numbers. Originally, a number used to be a means of counting, the natural numbers. Then we extend these numbers to instances of owing other people money, for instance, integers. Okay, and we're talking about here negative number, like, you owe someone money, well, then it's a negative on his books, his accounting books. Then he says, after that, we consider fractions when we need to split things like, 2 pizzas between 3 people. Okay, we get into those. And then he continues, he said, we then, skipping the algebraic numbers for the purposes of practicality, we use the real numbers to describe any length, the length of a diagonal of a unit square, for example, right? And again, you got to think about this as, the real numbers are the numbers that you would find on a number line. That means anything that can fit on a number line, fractions, any number between 2 integers or between 2 counting numbers, between 2 natural numbers, anything there is fine, even though it might not be a finite number, like pi ratio of the circumference to the diameter, 314. Well, it's what they call an infinite number, one that has no end. You keep having more and more decimals, and they're non-repeating decimals. So it's they call that an irrational number. Well, that would be included in there. You don't know the exact value, but it doesn't matter because 314 is between 313 and 315, and so it does fit on the number line. So that's why it's part of the real number system. The real number is what you would find on the number line. Okay, and then he ends up with a question. He said, but this is when our original definition of a number fails to make sense. When we consider complex numbers, which brings me to my main question, what is a rigorous definition of number? Okay, so this is the issue. The issue is that we don't know what a number is, or at least people have doubts, or they have a question. They want you to tell them, if you're a mathematician especially, to tell them, what do you mean by number? What is a number? I mean, after 3,000 years, we should know what a number is, right? Or the people who study to get PhDs, they had better know what a number is, right? Okay, so yes, they asked the question. Let's see what the answers are. These are some of the answers this individual got, okay? He got the following answers. This is the first one, or this was the one on the top, right? A basic question is, what would be the purpose of such a definition? So he's saying, we don't need definition. Let's just do math. I guess he's accusing the person who's asking the question of doing semantics, like let's do math. Well, why do we need definition? That's English. You should take a course in advanced English, or you got to talk to an English major or a librarian if you want to know what the word number means. But what is the purpose of such a definition? Would it clarify anything if we came up with a definition that, say, included quaternions and not matrices or analytic functions? Most of the usages of the term number are due to historical choices that have lived on. That's a very important point. That's true. We've changed the definition of number, of the word number, as we went through history. Originally, they were, we only started counting from one upwards, and nobody had a problem with that until we invented more concepts using numbers, especially when we went into geometry and we went into number lines and algebra and later on into calculus. Well, it really got complicated, and people said, well, is a function a number? Is an irrational number such as, square root of -1, which is the little letter I, is that a number? And so on. They started doing functions, and they started questioning the definition of the word number, of what the word number means. Okay, and he continues, the hardest part of coming up with a definition for number is to exclude. Why don't we call matrices, functions, or other similar things numbers? Things we see as primarily functions are not seen as numbers, but it is hard to exclude them with anything rigorous. In other words, this fellow's answering, we can't really define this because it's become so complicated that, we include everything under numbers, even though they don't have a real definition for the word number. Okay? So that's the first answer this fellow got. Here's a couple more. Okay. Oh, sorry, wrong one. Where is this? Here. Here we get a couple more. And it goes like this. There is no concrete meaning to the word number. If you don't think about it, then number has no concrete meaning. And if you ask around people in the street, what is a number, they are likely to come up with either example or unclear definitions. And in other words, people don't have any idea what the word number is. And we're not only talking about PhDs here, common folk. We're talking about PhDs as well. And you'll see that in a minute. In my thinking, a number is simply an object which satisfies some set of algebraic rules. In particular, these rules are typically constructed to allow an equation a solution. So this fellow, he thinks a number is just what comes at the other end of the equal sign in an equation. You solve it, you get a solution, that's a number. Okay? So that's his notion of number. He doesn't have a definition, but that's his notion, right? In mathematics, you don't really work with objects. No kidding. You work with the property. So we define an object, for example, a vector, in a certain context, linear algebra, as something that has a series of properties. In the example, you can add them, multiply by a scalar, create a base, and that is what we use. So this is you could call it a practical definition, a functional definition, an operational definition. In other words, however it's used, okay, we'll call that a number. That's what this fellow is saying. And I like another fellow who came on there and says, the best way to explain what property one is referring to is to give examples. In other words, if we're just going to define by giving examples, we have not defined. All we're doing is giving examples. Let me give you a for instance here. Let's say someone says, what does the word object mean for the purposes of physics? And the guy says, well, you know what an object is. It's a tree, a rock, a dog. That's an object. Well, yeah, but you haven't defined the word object. You haven't told me what an object is. So by giving me examples of what properties are, you're not telling me, still what you mean by number, if number is a set of properties, okay? So we still don't have a definition. And here are follow-up answers that came right after that. So you can get an idea where we stand on, and all these people, they have degrees, okay? So I want you to know that. And here they say, this is a deep and philosophical question. You are right. Kids start by learning to count things like 3 apples and 7 cars, but quickly build up to the real numbers, which we can make sense of by money and distances. When you start adding things like imaginary numbers, it gets less clear. Yeah, and so the question is, do any of these different categories of numbers qualify under the definition of the word number? That's the issue we're talking about. We're looking at the definition of the word number, okay? And that's important to keep in mind because people will say, well, you know, we've used this throughout hundreds of years. Are you going to change all this now? You know, they say, we know what a number is. You know, it's all these things that the mathematicians use. It's the real numbers and it's the irrational numbers. All those are numbers. And the question is, well, until you define the word number, we cannot decide that issue. We can only decide this issue objectively and only after we define the word number. Okay, the next one guy said, there is a general consensus that no such definition could possibly exist. Now that's interesting. Number is inherently a fluffy concept. And then another fellow puts, he says, Bertrand Russell in the early 20th century defined number as anything. Now listen to this. This is Bertrand Russell, right? He's a guru, right? As anything which is the number of some class. And now he continues, and the number of a class as the class of all classes, love all that are similar to it, where similarity of classes is defined by the existence of a bijection between them. My God. We had to go through all this just to find out what a number is. Did you get the definition? Do you now have it strong in your head after listening to Bertrand Russell? Do you know what a number is? Okay, here we have a fellow who wrote a thesis, a paper, an article. He's from the University of Pennsylvania. And he goes in there and he says, I'm going to tell you what a number is. I said, oh my God, finally someone who can tell me what a number is, okay? And obviously he's a mathematician. And his paper begins like that. I'm just going to go through the quick part of his paper. I'm not going to go through the entire paper because most of it are examples of, you know, how one type of numbers, as he regards them, turned into other types of numbers. How, you know, the irrational numbers became part of the complex numbers and so on, right? That kind of thing. And here he says the following, okay? Listen to this. This is a guy who's going to tell us what a number is. And he titles his paper, What Are Numbers? Great. We're going to find out right now. Okay, he says the aim of this course is to show what meaning has the notion of number in modern mathematics. Tell about the problems arising in connection with different understandings of numbers and how these problems are being solved. When a school student first meets mathematics, he or she is told that it is a science which studies numbers and figures. Okay, good. We started out on the right foot. Later in a college, she learns analytic geometry, which express geometric notions using numbers. So it seems that numbers is the only object of study in mathematics. Great. So far, we're on the right track. We're on the same page. True. If you open a modern mathematical journal and try to read any article, listen to this, okay? It is very probable that you will see no numbers at all. Instead, authors speak about sets, functions, operators, groups, manifolds, categories, etc. Nevertheless, all these notions in one way or another are based on numbers. In other words, ultimately there's a number that underlies these concepts, right? And the final result of any mathematical theory usually is expressed by a number. Great. So I think it is useful to discuss with math major students the question posed in the title, which is, what are numbers, right? I want to show what meaning can have the term number in modern mathematics. Finally, someone who's going to answer our question. Finally. Okay, and this is how he begins his paper. Okay, he says, this chain of subsequent extensions of the notion of number you must already know. Okay, I didn't like that too much. I'm supposed to know something. Okay, fine. The symbols occurring here are now the standard notations for the sets of natural, integer, rational, real, or complex numbers. quaternions, and octonions. Okay, fine. I want to discuss here the transition from one link of the chain to the next one and show that the ideas used in these transitions are working in other, sometimes unexpected and beautiful theories. Well, I don't care about beautiful theories, and I don't care how they link from, on a chain from one to the other. I want to know a definition of the word number, which is what he promised. He says, what are numbers? What is a number? I want to know that. That's what this thing is about. Well, he continues. He says, we can add natural numbers. This is how he continues with his paper. In other words, you won't find any definition before this, right? So I'm just going right through his paper to where I finally gave up and threw in the towel, right? He says, we can add natural numbers, but not always to subtract them. The integers can be multiplied, but not always divide. The wish to circumvent this inconvenience actually provoked the transition from natural numbers to integers and from integers to rationals. Recall how these transitions are made. If we want to subtract a natural number, m from the natural number, and then blah, 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 blah. And he just rants throughout his paper about how one type of number converted into another. He gives examples. He gives exercises to resolve them. He never answers the question that he put up there. What are numbers? This is the question that we wanted to have. So, wherever I've looked, so far I haven't found a definition of the word number. And so, at this point you say, well, is there anyone out there that knows what a number is? I just want a definition of the word number. That's all I'm asking for, okay? And here we have Wolfram, another famous site, Wolfram Math, okay? And Wolfram lays it on the line. He says the word number is a general term which refers to a member of a given, possibly ordered set. So it's a member of a set, whatever that means to you. I'm sure if I gave that definition, the word number, a member of a set, to the Greeks, ancient Greeks, they probably would have no idea what I'm talking about. What do you mean a set? What is it, a TV set or what? Okay, the meaning of number is often clear from context. Oh, so again, he's saying that we define by example. Does it refer to a complex number, integer, real number, etc.? Yeah, good question. Does it? We won't know until someone defines the word number. Then we will know. Okay, then we can match the definition against the examples and find out if the examples meet the specification of the definition. But right now, so far, we don't have any. And this is what you'll find under the word number in Wolfram. Okay, wherever possible in this work, the word number is used to refer to quantities. Oh, great! So number is a quantity, which are integers, and constant is reserved for non-integral numbers which have a fixed value. Now, I want to remind you the word integer means that it includes negative numbers and zero as well. So when he talks about integers, it's from negative infinity, as they call it, to through zero to positive infinity. Because terms such as real number, Bernoulli number, and irrational number are commonly used to refer to non-integral quantities, however, it is not possible to be entirely consistent in nomenclature. Okay. So again, after we look at Wolfram, we have no idea still what a number is, and that is quite frustrating there, right? Okay, let's see if the Encyclopedia of Mathematics. I looked it up there. Let's see if these guys know what a number is. Okay, and we go in there, the fundamental concept in mathematics, which has taken shape in the course of a long history development. That's what number is, right? It's a fundamental concept. The origin and formulation of this concept occurred simultaneously with the birth and development of mathematics. The practical activities of mankind on the one hand and the internal demands of mathematics on the other have determined the development of a concept of a number. Great, okay, that's how it came to be. What is a number? What are you talking about? The problem of the foundations of the concept of a number, and more broadly the foundations of mathematics, were clearly set out in the 19th century. This problem became a subject of mathematical logic, the intensive development of which continued into the 20th century. That's what they have on the definition of the word number. They have no idea. We don't know yet what they're talking about. What is this mysterious word number that they're talking about? And you might say, well, Bill, you're harping too much on semantics. Let's get on with it. Let's do some mathematics. Let's start using this stuff. You know, the word semantics really drives me up the walls because it means people didn't understand. You need to lay the foundations for any discipline. I don't care what you study. You study biology. What is biology about? It's the study of life. You had better define the word life. If you cannot define the word life, you are not a biologist. I don't care what degree they gave you, but you're not a biologist. You're only going to be a biologist if you can at least define the bread and butter of your discipline. If you're a paleontologist, they study extinction. That's what a paleontologist really does. All the rest of the stuff, picking bones and cleaning them, putting them in a museum, that's not paleontology. Paleontology is the study of death. Okay, you're a coroner. You got to figure out how these animals died in the past. Once we finish that, we're done with paleontology for the majority of people in the world. All the other guys who want to build, little skeletons there and put them in museums and name them, and that's a separate issue. Paleontologist studies extinction. If you don't know what the term mass extinction is or the term background extinction means, if you haven't defined it, you're not a paleontologist. You still don't know, what the bread and butter of your theory is. Yeah, correct. So, and in physics, we got the same problem. Physics is the study of objects. You can't do physics without an object. God comes into your universe, all-powerful God. He wipes out all the matter, every atom, every star, every galaxy. There's nothing there. What is happening? What is occurring? What's taking place? What experiment can you run, assuming you're the only object, right? There's nothing there for you to see, for you to deal with. You need objects to do physics. Therefore, the first term, the first word that you must define in physics is the word object. If you don't know what an object is, you're not a physicist. So we have no physicists on planet Earth in the last 2,000 years at least, or 3,000, probably even more, because no one has defined the bread and butter of physics, the word object. And likewise in mathematics, you need to define what a number is. If you don't know what a number is, what kind of mathematics are you doing? Are you going to call everything a number? Is a dog a number also? Yeah, it's a number one. Oh, great. What are we talking about? Are we going to talk about sets? You don't know what a number is, but you're going to talk about sets. You're going to talk about infinity. You're going to talk about zero. You're going to talk about imaginary number, square root of -1. Are you just going to bundle all these and say, well, they're all numbers. They're just different kinds of numbers. No, we need to define the word number if you're going to do mathematics, because it's the foundation, not because I want to do semantics. That's why people accuse me wrongfully and they send me to prison for saying this. It doesn't work that way. You got to define the bread and butter of your discipline. Numbers is the foundation, the bread and butter, the building blocks of mathematics. So please define the term number. And here we have a couple more. I'm just going to go through these two real quick. Let's see if I can get it in here. Okay. Here's Planet Math. And they say numbers an abstract concept which is not defined generally in mathematics. Well, they haven't defined it, but at least the guy's honest. He said, we haven't defined it. Maybe we used to know in the days of the Greeks what a number was. We don't know what it is after 3,000 years. We have no idea. Part of the reason, what the guy said before, through history, we've created so many new concepts within the field of mathematics that the word number has gotten bigger, bigger, and bigger. It encapsulates or encompasses more and more concepts that we've created. And so now it's very hard for them to come up with a definition that, includes all of these types of numbers. And so they, instead of defining the word number, what they've done is they've gone out there and they say, well, we'll call these integer numbers, and these others we'll call them the real numbers, and these others we'll call them the irrational numbers. The other one we'll call, the composite numbers or complex numbers. And that's the problem. The problem, they haven't defined the word number before they can do that, before they can divide them up into categories. Okay, so it says the numbers can be used for counting. Oh, okay, so they're kind of along my line of thinking. Yeah, you need to, numbers are used for counting, no doubt about that. In mathematics, one can define different kinds of numbers, okay? Usually the numbers which can be thought to be formed by gradually expanding the available system of numbers. So here they're talking about, again, expansion of the notion of what a number is. And of course, they include natural, integers, rational, real, and complex numbers, among others. And there's more, in there. For example, the irrational numbers are missing there for one. And you can put, I'm sure you can find more categories to fit in there. And it says, a usual applier of the mathematics and engineer probably believes that there are no other numbers than the complex numbers. Okay, so he might be wrong already, the engineer. Some school book may tell that the complex numbers form the widest possible field. Okay, however, the mathematicians know, they know better, right? That there exist infinitely many extension fields of the field C of the complex numbers. Example, the rational function field C sub x, or the formal Lorentz series field C double subscript x. Okay, that's a different matter if one wants to call the numbers the elements of the last fields. Okay, one of the things that struck me, which I underlined there, the word concept. I'm always interested in anyone who can define the word concept, and so I, wanted to see what these guys had to say about concept, to see if they had finally someone who has a definition for that. And I find that these guys don't even have a definition for that. They were referring to something called a concept lattice. In other words, they related the word concept to mathematics, and they go through all this rigmarole here that you can see all these equations. And by looking at that, you can get an idea why I stopped studying mathematics. I studied many courses in mathematics. I got a minor in mathematics, and eventually I dropped out. I was going to go for a major in mathematics. Finally dropped out because of this. You can see it becomes very, very abstract. You don't need to know what all those little things are. You can see that the wording already gives you an idea that's become very abstract. What does this have to do with anything? What does this have to do specifically with the real world, which is, physics? Physics deals with real stuff. This stuff is too abstract. And so, I just decided not to pursue a career in that field. Okay, so what is my definition? Do I have a definition? And again, I'm not a full-fledged mathematician. I can say I'm a partial mathematician. I did calculus, I did linear equations, I did a whole bunch of stuff out there, right? And at the time, I never thought about it in these terms. I just studied the math and said, oh, okay, yeah, I can do the problems, I can do the exercises and come up with solutions, fine. But I never thought in conceptual terms. What do we mean by number? I had to grow old to get to that point. Okay, it's just the way life works. So what does a number mean? The word number mean to Bill Gates? Okay, here it is. Okay, for the purposes of science, the word number is not a noun, it's not a verb. The word number means to count. It's a verb. Okay, only the natural numbers, or the what are known as counting numbers, those are the ones that qualify as numbers. Those are the only ones that meet the specification of the definition. So, you count, you move your hand up and down. 1, 2, 3, 4, 5, books, trees, rocks, whatever you're counting, it doesn't matter. Seconds on the clock. You move your hand. When you moved it 5 times, we put the number 5, which is a symbol that represents the number of times you moved your hand. All you're doing is adding up one by one the number of times that you moved your hand, and we replace it with something called a number. It's a symbol. You can put any symbol. The last week I showed you, the Romans had different numbering system, which is still used for centuries. 20th century, they put double X. Each X means 10, so they say 20th century. Fine. That was their numbering system. We use 1, 2, 3, 4, 5, the common numbers that we've inherited from the Arabs. And what do these numbers represent? The number of times you moved your hand, because that's what you're doing. You're counting something. And those are the only ones that qualify as numbers. How about the other numbers? The numbers all these people talk about. We have 0. we have infinity, we have irrational number, square root of -1. We have powers, we have fractions, we have decimals, multiplication, division, subtraction, addition. Do any of these qualify as numbers? We talk about sets, vectors, manifolds, fractals. Are these numbers? Do they qualify as numbers? And let's find out. If the definition is counting, then they don't. They don't because counting from 1 upwards, only those numbers qualify as numbers under the definition of numbers that I'm saying. You know, to count, just to count. And you can't count negatively. You can't count to 0. You can't count to infinity. You can't count to square root of -1. There's no such thing. So only those numbers which go from 1 upwards, that represent the number of times you moved your hand, only those qualify under the definition that I'm proposing, which is to count. That's the definition of the word number. It's a verb, not a noun. And here, let me show you this. Here we have a little statement, and that summarizes that. It said, all other types of numbers tacitly allude to or invoke a second number. That's the first problem we have for the definitions we have today. In other words, if you look at negative numbers, it invokes a second unidentified number from which the negative number is subtracted. How about natural numbers? Well, they are the numbers because they do not carry a positive sign in front of them. You know, it's just a number 1. It's not a +1. And it's not a number 5, it's or a +5. It's just a number 5. You counted up to 5. You did not put a plus in front of the 5 because what you did, you already added 1 to the 4 or 3 to the 2. You already performed that addition when you counted. All you're really doing is counting or tallying the number of times you move your hand. That's what you're doing. So there is no positive number. It's not a +5 because plus already involves an operation. Okay, so and which is the second thing up there. They are not numbers, but usually operations performed on numbers. So we have 2 problems with the number system that these people have. One is that it involves a second number. The other one is sometimes or most of the time, there are operations. There are other situations as well. Fractions, division, a ratio of 2 numbers. Again, you need 2. Decimals, a different way of writing fractions. Multiplication, addition, subtraction always require 2 numbers. And powers, roots invoke a number known as the exponent. You need something up there, okay? 3 to the 2nd power, you need that 2 up there above, it means you're going to multiply 3 times 3. That's what it means. And so we use a shorthand, we say 3 to the power of 2, but you need those 2 numbers, or you need at least to multiply 3 times 3. Either way you do it, you need 2 numbers. That's why it's not a number, because it's an operation performed on a number, and an operation always requires 2 numbers. So all these numbers, real numbers and so on, they're not numbers. The only numbers are 1 upwards. The counting numbers. That's the definition of number. Now you can do whatever you want with that. You can do whatever operation you want. You can add them, subtract them with other numbers. You can use 2 numbers to do whatever you want to do. But the definition of the word number has to remain fundamental. It's got to be part of the structure of mathematics, the foundations of mathematics. So you need to define the word number before you do anything else. And the definition is to count. That's what it is. Then after that, you can do whatever you want with the number. And that's why all these other categories that came after are not numbers. They are operations because they involve 2 numbers. And so here, let me show you this final thing here. Where is it? Let's see if I can find it here. These symbols, because these are typically considered as numbers, okay? You'll see it here, okay? So are any of these symbols numbers? And I'm saying none of these symbols are numbers. Here we have the 0. It's not a number because it represents a no count. You're not counting anything. And if the definition of the word number is to count, okay, A note count doesn't qualify under that definition. So 0 is not a number, period. How about infinity? Well, infinity is not a number because it means you are counting incessantly. You haven't stopped counting. Whenever you do, the moment you stop counting, we'll have a number. But as long as you continue counting, we'll let you do your counting and let us know when you stop. So infinity is not a number. It just means, oh, you haven't stopped counting. That's all infinity means. Means you, again, but it refers to a verb because it's saying that it's incessant counting. Okay? Either way you go, whether you go to positive or negative infinity, I don't know why they put the positive negative. I guess the only reason for that is to say, well, one goes in one direction, the other one goes in the other direction on the number line. And then the question is whether you can subtract negative infinity from positive infinity. Well, what number would you get? I guess, if you have positive infinity minus negative infinity, you would think that they're the same number, but they're not because you haven't stopped counting. You don't know if one guy stopped at plus 1,000,000, the other one stopped at minus 1,000. Then, plus infinity minus that 1,000 infinity is not going to be 0. Okay, so plus infinity minus infinity is not 0. And again, that's because they're not numbers. Pi, it's a ratio, so it doesn't qualify as a number. You need two numbers to specify pi. In this case, you're taking the circumference of a circle, whatever length you've got around that circumference, and you're relating it to its diameter. Okay, Euler's number, natural log 2.71828. It's a decimal. It's got decimals in there, and so it's not a number because a number is only an integer. Okay, in other words, it's only the natural number, the counting number. The 2 would qualify as a number. The 2.7, it's already not a number. It's a decimal, it's a ratio, and it's just a fraction that is represented in decimal format. That's all it is. Velocity of light, 300,000 kilometers per second. Not a number because it includes a unit, the kilometers per second. Number 3 is a number. 3 apples is not a number. Okay? Apples already includes a unit. You're talking about something else. You're applying the number 3 to something else. So a number is only when it stands alone, not when it's accompanied by a unit. Again, the little I there, it's the square root of -1. It's not a number because it's an operation, a root in this case, performed on a negative number. Which is not a number to begin with, because -1 is not a number. The 1 would be a number, but not the -1. G, the gravitation here on Earth, that's the symbol we use, 9.8 meters per second square. That's not a number again because it's got a ratio there. The 0.8 is the ratio part. Gravitational constant, same thing. It's got 67259 there. It's also got a unit behind it. Same for Planck's constant, the H. So none of these qualify as numbers. These are operations. These are fractions. All these things that you see there all require 2 numbers, all of them. So they don't meet the definition of number. Okay, and that's all I'm saying. I'm saying first we have to define number, then you can do whatever you want. You can use them. I'm not saying you can't use them in an operation. I'm not saying that you can't add or subtract and all that they've done in the last 10,000 years is nonsense. No, I'm just saying let's define the word number so that we know what a number is, because we need it for the foundations of arithmetic and we need it for the foundations of mathematics. I'm saying number is just the verb to count. Boom, 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 boom. Counted 4. I replace that movement of my hand with a number 4, with a symbol 4, and we say you counted 4 times, and we'll call that the number 4. We turn that verb into a noun. Okay, that's a number. Period. Now we can do whatever we want with that. You can say 4 minus 3. That's an operation. You need 2 numbers. 4 to the square. You can square it or you can root it. You can say the square root of 4. You can do any operation you want, but let's get the definition in there first. Okay, and that's the story for today. Again, if anyone knows a little bit of what might be causing some of my video and my sound problems, I'd really appreciate you getting in touch with me. I replaced my computer, have a new one here, and seems to be working fine. But last time I saw a little glitch there at the end where it became blurry. One more time, I'll put this up one more time for those who missed it. Where is it? Here it is. Can't find it now. Oh, here it is. We're going to be at Boris, June 6th to 9th. There's going to be the 7th Rational Physics Conference. And next week, Sunday, where is it? If I can find it. Next Sunday, we are going to be in the public space with JFG. We're going to be talking about black holes, more than likely. His program is at 1900 hours Eastern Standard Time because that's Quebec time. That's the time he has his show. Over here in Germany, it's 1 o'clock in the morning. So I don't know why I contract for these things, but that's what I did. So, I invite you to be there, okay? And you'll hear what I have to say about black holes. Peter might be there. I think he's been invited as well. That's still not confirmed to me, but I think he will be there. And so if you want to hear a good discussion, well, tune in next week, 1900 hours Eastern Standard Time on the public space run by JFG. Okay, folks. I'm going to continue probably on, on Wednesday. I'll continue with the word point. And that's another monster. And that is more related to physics because just about everything in physics deals with a point. And I guess we'll see why on Wednesday at least. We'll see you then. Bye-bye.